In today's documentary, we'll dive into the fascinating journey of how electricity was discovered. Before Earth had oceans, before the sun even began to shine, electricity already existed. Right now, as you listen to this, something is happening inside your body that you cannot feel, cannot see, and cannot stop. Your heart just beat. Not because a muscle decided to squeeze, not because you willed it, but because a tiny electrical signal generated by a cluster of cells called the sinoatrial node fired an impulse at roughly 60 to 100 times per minute, every single minute of your entire life, and it will not stop until you are dead. You did not ask for that. You cannot override it. You cannot understand it fully, even now, in the 21st century, even with all of our instruments and equations and particle accelerators and quantum computers. The force that keeps you alive is the same force that tears a tree apart in a thunderstorm. The same force that allows you to read a text message, that allows surgeons to restart a stopped heart, that allows a child to see light from a star 400 light-years away through a telescope. It is electricity. And here is the most extraordinary thing about it. For the vast majority of human existence, for 200,000 years of Homo sapiens walking this earth, building fires, carving tools, telling stories, burying their dead, painting on cave walls, inventing agriculture, raising empires, nobody had the slightest idea what electricity actually was. They felt it, they feared it, they worshipped it. The ancient Egyptians called the electric catfish of the Nile the thunderer, and they described it in texts dating back to 2750 before the Common Era as the protector of all other fish. The ancient Greeks felt shocks from electric rays in the Mediterranean, and they called these creatures narca, the word from which we eventually derived the word narcotic, because their shocks numbed the body like a drug. Roman soldiers reported that stepping on an electric ray in shallow water could knock a man off his feet. And yet not a single one of these people, not the Egyptian priests, not the Greek philosophers, not the Roman legionnaires, could tell you what was actually happening when those fish delivered their terrifying jolts. They were standing at the edge of one of the most profound mysteries in the history of science, and they had no idea that the jolt from that fish and the flash in the sky were the same thing. No idea that that same thing would one day reshape every civilization on Earth. No idea that the secret hiding inside that fish, inside that storm, was the fundamental glue of all matter. The interaction between charged particles that holds every atom in your body together right now. This is the story of how humanity discovered electricity. Not invented it, discovered it. Because electricity was not invented, it is older than the Earth. It is older than the solar system. The electrical force, the electromagnetic force, is one of the 4 fundamental forces of the universe, and it has existed since the first fraction of a second after the Big Bang, approximately 13.8 billion years ago. We did not create it. We stumbled upon it, misunderstood it, argued about it, accidentally almost killed ourselves with it, and finally, over the course of roughly 2,500 years, began to understand it well enough to harness it. This is that story, and it is stranger than you think. Part 2, Amber and the Dawn of Wonder, 600 before the Common Era. Let us begin on the coast of the Aegean Sea, in a city called Miletus, which today lies in ruins on the western shore of what is now Turkey. The year is approximately 600 before the Common Era, which means we are talking about 2600 years ago. And in this city lives a man who is, by most accounts, the first philosopher, the first person in recorded history to attempt to explain the natural world through reason rather than through mythology. His name is Thales of Miletus. Thales is a fascinating figure. He is the man who, according to legend, was so absorbed in studying the stars that he walked into a well, prompting a Thracian servant girl to laugh at him. A joke that has survived 2.5 millennia and which philosophers still retell today as a kind of good-natured warning about the dangers of pure abstraction. He predicted a solar eclipse. He devised theories about the nature of matter. He is credited with founding the traditions of both Western philosophy and Western mathematics. And one day he picked up a piece of amber and rubbed it against a piece of fur. Amber, for those unfamiliar, is fossilized tree resin, the hardened sap of ancient trees, sometimes containing trapped insects or plant material, polished by millennia into a beautiful translucent golden yellow stone. The ancient Greeks called it elektron. And when Thales rubbed a piece of it against fur, he noticed something remarkable. Small, lightweight objects, dust particles, pieces of chaff, tiny feathers were attracted to the amber. They moved toward it as if pulled by an invisible hand. Thales did not understand why. He theorized incorrectly that amber must have a soul, must be somehow alive, because only living things could cause motion. He was wrong about the mechanism, but he was right to be astonished. What Thales had observed was static electricity. Here is what was actually happening at the atomic level, in terms that would not be articulated for more than 2,000 years. Every atom in the universe contains a nucleus made of protons and neutrons, surrounded by electrons in orbital shells. Protons carry what we define as positive charge. Electrons carry negative charge. In neutral atoms, the number of protons and electrons is equal, and the charges cancel out. But certain materials, like amber, have electrons that are loosely held in their outermost shells. When you rub amber against fur, the friction gives electrons enough energy to transfer from the fur to the amber. The amber gains extra electrons. It becomes negatively charged. Nearby lightweight objects, which may have a slight positive charge or whose charges can be redistributed, are attracted to the now charged amber through what we call the electrostatic force. The electrostatic force. This is one of the oldest known observations in the history of physics, and it deserves a moment of genuine astonishment. What Thales observed was the consequence of one of the 4 fundamental forces that govern the entire universe, the electromagnetic force. And this force is staggering in its power. The electromagnetic force between 2 electrons is approximately 10 to the power of 42 times stronger than the gravitational force between them. Let me say that again. 1 followed by 42 zeros times stronger. The reason gravity seems so powerful in your everyday experience is simply that gravity acts on everything with mass, and the Earth has an enormous amount of mass pulling you down. But the electromagnetic force is almost incomprehensibly more powerful. The reason you can sit in a chair without falling through it is not gravity. It is the electromagnetic repulsion between the electrons in the atoms of your body and the electrons in the atoms of the chair. Thales felt the edge of that force when he rubbed a piece of amber against fur, and he called it nothing, because the word for it did not yet exist. For the next 2,000 years, the story of electricity is largely a story of very smart people noticing strange things and failing to understand them. The ancient Greeks and Romans used electric eels and electric rays as medical treatments. The Roman physician Scribonius Largus, writing around 46 of the Common Era, recommended that patients with gout or chronic headaches place their feet on a live electric ray. A living torpedo ray, which can deliver discharges of up to 200 volts, was essentially a medical device, and it was not entirely useless. The numbing effect of the electrical discharge did temporarily relieve pain. They had stumbled into electrotherapy without the slightest understanding of electricity. The ancient Parthians, a civilization that ruled much of what is now Iran and Iraq from roughly 250 before the Common Era until 224 of the Common Era, may have gone even further. In 1938, a German archaeologist named Wilhelm König was examining artifacts in the Baghdad Museum when he found something that would become one of the most debated objects in the history of science. The artifact consisted of a clay jar, approximately 13 to 14 centimeters tall, containing a copper cylinder made from a rolled copper sheet, with an iron rod suspended at the center. The jar was sealed with bitumen, a natural asphalt-like substance. König looked at it and thought he recognized it. He thought it looked like a battery. What is now called the Baghdad Battery, or the Parthian Battery, dates to somewhere between 250 before the Common Era and 224 of the Common Era. König published his theory in 1938, suggesting that if the jar were filled with an acidic liquid, vinegar perhaps, or fermented fruit juice, the iron rod and copper cylinder would form what is called a galvanic cell. A galvanic cell produces electrical current through a chemical reaction. Iron and copper have different electrode potentials. When separated by an acidic electrolyte, electrons flow from one metal to the other, generating a current. Experimental replicas filled with lemon juice have been shown to generate between approximately half a volt and 1 volt, and when connected in series, multiple jars have demonstrated enough current to perform minor electroplating. The 1985 television program Mythbusters conducted one of the most famous modern replications. Using lemon juice as the electrolyte, connected jars produced approximately 4 volts, enough in principle for small-scale electroplating and electrostimulation. But here is the complication. There is no direct archaeological evidence that the Parthians used these jars for electricity in any deliberate sense. Some archaeologists believe they were used to store sacred scrolls, pointing to similar bitumen-sealed jars found at nearby sites. Others note that there are no known electroplated objects from the same period, making the electroplating theory difficult to confirm. And still others point out that even if these devices did accidentally produce electricity, the Parthians may have had no theoretical understanding of what they were generating. The Baghdad battery represents the deepest and most tantalizing possible question in the history of electricity. Did ancient people discover and use electrical current 2,000 years before Alessandro Volta built his famous pile? The honest answer, as of today in 2026, is we do not know. The artifact is real. The chemistry works. But whether the people who made it knew what they had, whether this was discovery, accident, or something in between, remains genuinely uncertain. The original artifact, once housed in the National Museum of Iraq, was reported missing after the looting of the museum during the 2003 invasion of Iraq, adding a layer of tragedy to the mystery. What is not uncertain is this. Whatever the Parthians may or may not have known about electricity, the knowledge, if it existed, did not spread. It did not survive. It did not propagate through the civilizations that followed. And so, for another millennium and a half, the world remained in the dark. Part 3. Gilbert and the word that changed everything. 1600. The year is 1600 of the Common Era, and England is ruled by a 66-year-old woman who has, by this point, been queen for 42 years. Elizabeth I is aging, brilliant and complicated. Her court is a place of extraordinary intellectual energy. Shakespeare is 46 years old, still writing. Francis Bacon is 39. And the Queen's personal physician, a man who will never be as famous as either of them, but whose contribution to human knowledge is in many ways more significant, has just published what is arguably one of the most important scientific books of the pre-modern era. His name is William Gilbert, and his book is called De Magnete, On the Magnet. De Magnete is 6 volumes. It covers magnetism and electricity in a rigorous, systematic, experimental way that is almost without precedent in the Europe of its time. Gilbert makes a careful distinction between magnetic force, which he studies extensively in lodestones, and the attractive force generated by rubbing amber and similar materials. And in doing so, he invents a word. He coins the Latin term electricus, meaning of amber, or like amber, from the Greek word elektron. From electricus comes electric. From electric comes electricity. You're using a word invented in 1600 by a doctor who died 2 years later of plague. But Gilbert does more than name the phenomenon. He builds the first scientific instrument for detecting electrical charge, a device he calls the versorium. It is a small, lightweight needle mounted on a pivot, much like a compass needle, and it deflects when brought near a charged object. It is, in essence, the world's first electroscope, and using it, Gilbert tests dozens of materials, cataloguing which ones can be electrified by rubbing and which ones cannot. He identifies amber, glass, sulfur, sealing wax, and several gemstones as electrics. He establishes a clear experimental method. Rub the material, bring the visorium close, observe the deflection. It is systematic. It is reproducible. It is science in a form we would still recognize today. Gilbert also argues, crucially, that the Earth itself is a giant magnet, which is correct, and that the compass needle points north not because of some mystical connection to the pole star, but because of the Earth's magnetic field. This may seem obvious today. At the time, it was revolutionary. He was, in short, a man operating about 2 centuries ahead of the conceptual tools available to him. Gilbert died in 1603. He did not live to see what his naming of electricity would eventually unleash. But the name stuck, and names have power. They make things thinkable, discussable, pursuable as concepts. Once electricity had a name, it had an identity. And once it had an identity, people could begin to investigate it deliberately. The decades following Gilbert's death see a slow acceleration of electrical investigation across Europe. In 1660, a German engineer and natural philosopher named Otto von Guericke, already famous for his spectacular demonstration of atmospheric pressure using the Magdeburg hemispheres, in which 2 teams of horses famously failed to pull apart 2 copper hemispheres held together only by a vacuum, turns his attention to electricity. Von Guericke builds what is possibly the world's first electrostatic generator. He takes a globe of sulfur, mounts it on a rotating shaft, and holds his hand against the globe as it spins. The friction between his hand and the sulfur globe generates significant static charge. He is able to attract and repel lightweight objects, and crucially, he demonstrates that electricity can not only attract, but also repel. This is new. Thales had only observed attraction. Von Guericke shows that charged objects can push other charged objects away. He also observes something strange. In a dark room with the charged sulfur globe, he can see a faint glow, a visible light produced by the electrical charge. He does not understand it, but he has, without knowing it, observed the earliest recorded laboratory production of electrical light. The principle he has stumbled upon, the excitation of gas or material by electrical discharge to produce light, will eventually become the basis of neon signs, fluorescent tubes, and plasma screens. In 1660, he simply found it strange and wrote it down. By 1700, English scientists are making further advances. Stephen Gray, a pensioner at the Charterhouse in London, discovers in 1729 one of the most important early principles of electricity, that electrical charge can travel. Gray suspends a boy from the ceiling by silk ropes, silk being a poor conductor, and touches the soles of the boy's feet with a charged glass tube. He then brings a small piece of gold leaf near the boy's nose. The gold leaf leaps toward the nose. The charge had travelled the entire length of the boy's body. Gray has discovered, through the medium of a suspended child, that electricity is not just a local effect confined to the rubbed surface, but a force that can be transmitted through certain materials over a distance. He calls materials that transmit electricity conductors, and those that do not insulators. These are still the terms we use today. A French aristocrat named Charles Dufay, building on Gray's work in 1733, discovers something else foundational. He realizes that there are not one but two kinds of electrical charge. He calls them vitreous electricity, from the Latin for glass, and resinous electricity, from substances like amber and wax. Like charges repel, unlike charges attract. This is the fundamental rule of electrostatics. He does not understand why, but he observes it consistently. Today we call his vitreous electricity positive charge and his resinous electricity negative charge. The names changed. The observation was correct. Part 4. The Leyden Jar, the first capacitor and the first dangerous experiment. The year is 1745. In a laboratory in the small city of Taming in Pomerania, a region now divided between Germany and Poland, a German cleric and scientist named Ewald Georg von Kleist is trying to store electrical charge. He takes a small medicine bottle, fills it partly with alcohol, pushes a nail through the cork and connects the nail to his electrostatic machine. When he picks up the charged bottle and touches the nail, something extraordinary happens. He receives a shock of such violence that his arm goes numb. Von Kleist has accidentally invented the capacitor. He has built what will become known as the Leyden Jar, independently and slightly earlier than the Dutch physicist Peter van Musschenbroek at Leiden University, who duplicates the discovery in 1745 and 1746. The name Leyden Jar sticks because von Kleist's work was less widely publicized initially, and because the Abbé Nollet, a French physicist with great promotional flair, advertised Musschenbroek's version to wealthy European science enthusiasts. Von Kleist, the actual first discoverer, is largely forgotten by history. Science is sometimes unkind in its naming. What is the Leyden Jar at a physical level? At its simplest, it is a glass jar coated on both the inside and outside with metal foil. One conductor on the inside, one conductor on the outside, separated by the glass which acts as an insulator. You connect the inner foil to an electrostatic generator and charge accumulates. The outer surface, typically held in the experimenter's hand, develops an equal and opposite charge through induction. The two charged surfaces facing each other across the insulating glass create what we now call an electric field between them. The energy is stored in that field. When you connect the inner and outer conductors by touching the nail or chain on top of the inner foil while holding the outer foil, the stored charge releases all at once in a violent, instantaneous discharge. This discharge is, in modern terms, nothing more than the behavior of a capacitor. The energy stored in a capacitor is equal to 1/2 times the capacitance times the voltage squared. Expressed in words, it equals 1/2 multiplied by C multiplied by V to the power of 2. The energy density can be extraordinary for a glass jar, which is why the early recipients of a Leyden jar discharge were sometimes knocked to the ground. The Leyden jar becomes, almost immediately, one of the most sensational scientific demonstrations of the 18th century. The Abbé Nollet performs demonstrations before King Louis XV of France. He connects approximately 180 royal guards in a circle, joining hands, and then discharges a Leyden jar through the line. 180 soldiers jump simultaneously. The king laughs. The soldiers presumably do not laugh. The spectacle of electricity as public entertainment has begun. In another famous demonstration, Nollet sent a discharge through a line of Carthusian monks connected by iron wires, reportedly more than a mile in total length, to observe that the shock was felt simultaneously at every point in the chain. He had, in doing so, made one of the earliest demonstrations that electrical signals travel at extraordinarily high speed, far faster than sound, far faster than anything the 18th century had a conceptual framework for. But the Leyden jar is not merely a party trick. It becomes the primary experimental tool for studying electricity for the next several decades. It allows scientists to accumulate charge, store it, and discharge it in controlled experiments. It is the world's first rechargeable energy storage device in the loosest possible sense. And it puts electricity in the hands of one of the most remarkable minds of the 18th century. A man who, at this point in his life, is primarily known as a printer, a postmaster, and a statesman. Benjamin Franklin is interested in everything. He is 40 years old in 1746 when he first encounters the Leyden jar through a demonstration and written description, and he is immediately consumed by it. In one of the more colourful episodes of American scientific history, he attempts to recreate the Leyden jar experiment at home, and, upon receiving the full discharge of 2 jars connected together, is knocked senseless. He wrote afterward that he neither saw the flash, heard the report, nor felt the stroke. He had been briefly knocked unconscious by a homemade capacitor in his own kitchen. He noted, with characteristic dry humour, that the main experiment he concluded from this event was the ease with which too much zeal can knock a philosopher on the head. Franklin recovers. He keeps experimenting. And over the next several years, he develops 2 ideas that transform the science of electricity. The first is theoretical. He proposes that electricity consists of a single fluid, and that what Dufay had called 2 kinds of electricity is better understood as a surplus or deficit of this single fluid. A body with too much of the fluid is what Franklin calls positive. A body with too little is negative. He gets the names right, but he gets the direction wrong. He assumes the fluid flows from positive to negative, while in reality electrons, which would not be discovered for another 150 years, flow from negative to positive. This directional confusion still haunts us today. When engineers talk about conventional current flow, they are using Franklin's convention, the direction opposite to the actual movement of electrons. We have essentially been using a backwards convention for 250 years, because changing it at this point would require rewriting almost every textbook on Earth. Franklin's second contribution is far more dangerous to arrive at, and far more immediately useful. He wants to know if lightning is electricity, not metaphorically, not as a poetic comparison. Literally, is the giant crackling discharge in the sky the same phenomenon as the spark from a Leyden jar? In June of 1752, in Philadelphia, though the exact details have been debated by historians, Franklin reportedly flies a kite during a storm. The kite string is made of hemp, which conducts electricity when wet. At the bottom of the string, a metal key is attached. The key is connected to a Leyden jar by a dry silk thread, which insulates Franklin's hand from the charge. During the storm, as the dark clouds pass overhead, Franklin notices the fibers of the hemp string begin to stand on end, charging with static electricity from the charged atmosphere. He brings his knuckle close to the key. A spark jumps. Lightning is electricity, not similar to electricity, not analogous to electricity. The same thing, physically, fundamentally identical in mechanism to the spark from a Leyden jar, differing only in scale. A typical lightning bolt involves a potential difference of approximately 300 million volts, carries a peak current of 30,000 amperes, and releases energy in the order of 1 to 5 gigajoules, enough to power a 100-watt light bulb for approximately 25 million seconds, or roughly 8 months. The spark from Franklin's Leyden jar might have been a fraction of a volt. The principle was identical. What Franklin has done is something that happens rarely in the history of science. He has unified two phenomena that appeared completely different on the surface and shown them to be manifestations of the same underlying process. The rumbling giant in the sky and the tingle on a combed hair were the same thing. This is the kind of insight that reconfigures a civilization's relationship with nature. It demystified lightning. It took something that had been the weapon of gods, Zeus's thunderbolt, Thor's hammer, the wrath of Yahweh, and placed it in the category of natural phenomenon subject to scientific understanding. This was not merely a scientific discovery, it was a philosophical revolution. Franklin follows this discovery with one of the most practically consequential inventions in history, the lightning rod. A metal rod mounted at the top of a building connected to a wire that runs down the outside of the structure and into the ground. When lightning strikes, as it reliably seeks the highest conductive point, the charge is conducted safely through the wire into the earth, rather than through the building itself. The invention is simple. Its impact is enormous. Fires caused by lightning strikes had historically destroyed countless buildings, including churches, barns, and entire neighborhoods. The lightning rod essentially solves this problem. It is one of the clearest examples in history of a fundamental scientific discovery, that lightning is electrical, leading almost immediately to a life-saving practical application. And there is a delicious irony attached to it. In France and England, there was initially a debate about the shape of the lightning rod's tip. Franklin advocated for a pointed tip, which he believed would draw off charge gradually and silently from storm clouds. British scientists, partly out of anti-American sentiment during the period of the American Revolution, advocated for a blunt-tipped rod. King George III reportedly ordered blunt tips on the Royal Society and his own palaces. The British astronomer Royal Neville Maskelyne defended blunt rods in part by noting in a remark that became famous that he would not change his scientific opinion merely because the king wished it. The pointed tips turned out to be more effective in practice. Franklin had been right, and British royal politics had briefly influenced the design of lightning protection technology. Part 5. The frog that started a revolution. Galvani and the birth of bioelectricity. We are now in Bologna, Italy. The year is 1780, and in a laboratory at the University of Bologna, a physician and anatomist named Luigi Galvani is doing what he always does, studying the anatomy of frogs. He has been dissecting and examining frogs for years, studying their nervous systems, their muscles, the structure of their bones. He is meticulous, scholarly, and genuinely curious about the relationship between electricity and living tissue. He already knows that a Leyden jar can make a dead frog's leg twitch. But on this particular day, he sees something that will kick off one of the most famous scientific disputes in history and lead, through a long chain of consequences, to the invention of the battery, the development of neurophysiology, and, through a strange cultural detour, to a novel about a monster. Galvani's assistant is working at a table nearby with an electrostatic generator. On the same table there is a dissected frog, legs removed at the spine, sciatic nerve exposed. The assistant's metal scalpel accidentally touches the exposed nerve. At the exact moment of contact, the electrostatic generator across the room sends a spark, and the dead frog's leg kicks. Not a twitch, not a subtle flicker. A violent, muscular kick, as though the frog were alive and trying to leap. Galvani stares at this. He thinks very carefully about what he has just seen, and then he begins to experiment. He works for the next 11 years. He exposes frog legs to storms, connecting them to lightning rods. He hangs frog legs on brass hooks from iron railings during bad weather. He tries dozens of combinations of metals. He works with the frog legs indoors, on clear days, with no external electrical source at all. And he observes that under the right conditions, particularly when two different metals simultaneously touch the nerve and muscle of the frog, the leg twitches without any external source of electricity whatsoever. On clear days, in closed rooms, with no Leyden jar, no electrostatic machine, nothing. Galvani's conclusion is breathtaking in its ambition, and, as it turns out, half right and half wrong. He concludes that living tissue contains its own electricity. He calls it animal electricity. He publishes his findings in 1791 in a paper titled De Viribus Electricitatis in Motu Musculari Commentarius, Commentary on the Electrical Forces in Muscular Motion. He argues that the brain generates electrical fluid, the nerves carry it to the muscles, and the muscles store it like a Leyden jar. When the circuit is completed by a metal arc touching both nerve and muscle, the stored charge flows and causes contraction. He is immediately attacked by a colleague and rival who will ironically become his greatest legacy. Alessandro Volta is a professor of experimental physics at the University of Pavia. He is Galvani's contemporary, his compatriot, and initially his admirer. But when he reads Galvani's paper, something nags at him. He repeats the experiments. He confirms the results. The frog's leg does indeed twitch when two different metals bridge the nerve and muscle. But Volta has a different interpretation. He doesn't believe the frog is generating the electricity. He believes the two different metals, the iron hook and the brass railing, say, or the iron and the bronze, are generating the electricity. The frog, in Volta's view, is not the source. It is merely the detector. To test this, Volta begins experiments with metals alone. No frog, no living tissue. He places different metals in contact with each other and with salt solutions. Silver touching copper, separated by brine-soaked cloth. Iron in contact with zinc. He discovers that any two dissimilar metals, separated by a conducting liquid, an electrolyte, produce a measurable electrical potential difference. The metals alone, reacting chemically with the electrolyte, generate electricity. This is what had been making the frog twitch. The two metals were creating the current. The frog's body was merely conducting it, completing the circuit, and the still-living nerve cells in the freshly dissected tissue were firing in response. The debate between Galvani and Volta is one of the most scientifically productive disputes in history. Both men are right, and both men are wrong, and the resolution of the argument takes decades. Galvani is wrong that the frog itself generates the electricity driving the contractions in his bimetallic experiments. Volta is right about that. But Galvani is right that living tissue generates its own electricity. He eventually proves this in an extraordinary series of experiments without any metal, touching the nerve of one frog directly to the muscle of another and observing contractions. Tissue-generated electricity is real. We now understand it completely. Your neurons are firing electrical signals right now as you listen to this, entirely on their own, powered by chemical gradients across cell membranes. A process of ion channels and electrochemical pumps that would not be fully understood until Alan Hodgkin and Andrew Huxley published their landmark mathematical model in 1952. Galvani never saw vindication in his own lifetime. He died in 1798, 2 years after publishing his most convincing evidence for animal electricity, by which time Volta's battery had so captivated the scientific world that most of Galvani's insights were temporarily overshadowed. But history has given him his due. We call the galvanic cell a galvanic cell in his honor. We speak of galvanized metal, zinc-coated iron, named for the process of coating metals using electrical current. The word galvanized, in the sense of being startled into action, galvanized into motion, comes from the sight of those frog legs kicking. The entire field of electrophysiology, the study of the electrical properties of living cells, traces its lineage directly to his laboratory in Bologna. And then there is the other legacy. Galvani's nephew, Giovanni Aldini, took his uncle's work on the road. He performed public demonstrations of what he called galvanism across Europe. In London in 1803, Aldini obtained the body of a recently executed murderer named George Forster, and in front of a packed audience of physicians and curious spectators at the Royal College of Surgeons, he applied a voltaic pile to the corpse. The jaw clenched, the eye opened. One hand rose as if in supplication. The legs kicked. According to contemporary accounts, one spectator fled the room in terror. Another reportedly died of shock shortly afterward, though this claim has never been confirmed. The London Times covered it. The event became a sensation. One person who heard about it and about the broader debate around animal electricity and whether the force in living tissue was distinct from ordinary electrical fluid was a 19-year-old woman named Mary Godwin, who would later become Mary Shelley. In 1816, during the famous Year Without a Summer, caused by the eruption of Mount Tambora in Indonesia and the subsequent global temperature drop from volcanic ash in the stratosphere. Mary Godwin is stuck inside a villa near Lake Geneva with Percy Shelley, Lord Byron, and the physician John Polidori. They tell ghost stories to pass the dark, cold evenings. Byron challenges them to write one. Mary Godwin takes the question of galvanism, the question of whether a dead body can be made to live again by electricity, and writes Frankenstein or the Modern Prometheus, published in 1818, the first true work of science fiction, born directly from the debate between Galvani and Volta. Part 6. The Voltaic Pile. The battery that changed everything. Volta wins the argument, at least in the short term, and in winning it, he produces what many historians consider the single most important invention in the history of electricity. In 1799, building on his experimental proof that dissimilar metals in an electrolyte generate electrical potential, Alessandro Volta constructs a stack of alternating discs of zinc and copper, each pair separated by cardboard soaked in salt water or dilute sulfuric acid. He stacks them into a column. He connects a wire to the top disc and a wire to the bottom disc. Current flows continuously, steadily, without stopping. This is the voltaic pile, and its implications are almost impossible to overstate. Before the voltaic pile, every electrical experiment had been conducted with static electricity from friction machines or the brief, violent discharge of Leyden jars. Static electricity is difficult to control, dangerous to store, and produces only momentary currents. The voltaic pile produces a continuous, steady, controllable current. For the first time in the history of science, electricity is something you can turn on and leave running. You can regulate it, you can direct it, you can study its effects over time. It is, in the most fundamental sense, the first true battery. And like the Leyden jar before it, it is something far more significant than a scientific instrument. It is a key. Volta writes to the Royal Society of London in March of 1800, a letter that will be read as one of the foundational documents of modern electrical science. The Royal Society is so impressed that they immediately invite Volta to London to demonstrate his pile. And the following year, in 1801, Volta demonstrates his invention before the French Academy of Sciences, before Napoleon Bonaparte himself. Napoleon is so captivated by the demonstration that he interrupts several times to ask questions, eventually calling Volta to his side and asking to see the pile up close. Napoleon made Volta a Count of Lombardy and a senator of the Kingdom of Italy. He understood with the instinct of a general that this device represented a new kind of power. The unit of electrical potential, the volt, is named for Alessandro Volta. Every time you read 1.5 volts on a battery or 220 volts on an electrical outlet, you are invoking the name of a professor from Pavia who spent years arguing with a colleague about a twitching frog leg. The voltage of a battery, at its most fundamental level, is a measure of the energy available per unit of charge, expressed in joules per coulomb. 1 volt equals 1 joule per coulomb. The voltaic pile produced modest voltages. Its output depends on the number of cells and the specific metals used. But this was entirely sufficient to open up an entirely new era of electrical experimentation. The immediate consequences of the voltaic pile are breathtaking. Within weeks of the pile becoming known, scientists across Europe are building their own versions and performing experiments that would have been impossible before. In May of 1800, just 2 months after Volta's letter to the Royal Society, 2 English chemists named William Nicholson and Anthony Carlisle use a voltaic pile to decompose water. They dip 2 wires from the battery into water and observe bubbles forming at each wire. The bubbles at one wire are hydrogen. The bubbles at the other are oxygen. Water, which for millennia had been considered one of the fundamental elements of the universe, going back to Thales himself, is not an element at all. It is a compound of 2 gases separable by electricity. This process, electrolysis, becomes one of the most important techniques in chemistry. Humphrey Davy, the brilliant and flamboyant Cornish chemist at the Royal Institution in London, takes the voltaic pile and uses it to discover new elements. In 1807, using a massive voltaic pile, the most powerful battery yet constructed, consisting of 250 pairs of metal plates, Davy passes current through molten potash and isolated for the first time the element potassium. Days later, he isolates sodium in the same way. Over the next 2 years, using electrolysis, he isolates calcium, barium, magnesium, strontium and boron. 6 elements discovered through the direct application of the voltaic pile. Elements that had been present in substances that humans had been using for thousands of years, completely unrecognized. Electricity had become a microscope for the structure of matter. Working in Davy's laboratory as a young bookbinder's apprentice turned scientific assistant was a man who would, within a few decades, accomplish the greatest single feat in the history of electrical science. His name was Michael Faraday. Part 7. The Compass That Moved, Ørsted and the Birth of Electromagnetism. Before we reach Faraday, we must stop in Copenhagen, Denmark, in the year 1820. Because something happens in a lecture hall at the University of Copenhagen that is so unexpected, so completely at odds with everything scientists believed they knew, that it will force a fundamental rethinking of the relationship between two forces that had previously been considered entirely separate. Hans Christian Ørsted is a Danish physicist and professor. He is a follower of the philosophical tradition of Naturphilosophie, a German romantic intellectual movement that believed in the fundamental unity of all natural forces. For years, Ørsted has suspected, on theoretical and philosophical grounds, that electricity and magnetism must be related. He has no experimental evidence for this. His colleagues are largely skeptical. The general view of the scientific community in 1820 is that electricity and magnetism are two completely separate phenomena with no connection to each other. Electricity attracts and repels charged objects. Magnetism attracts and repels iron. Different forces, different mechanisms, case closed. One evening, accounts differ on whether this was during an actual lecture or during preparation for one. Ørsted is setting up a demonstration involving an electrical circuit. He places a compass near a wire carrying current from a voltaic pile, and the compass needle moves. Let us be absolutely clear about why this is extraordinary. A compass needle is made of iron and responds to magnetic forces. A wire carrying an electrical current is not a magnet. There is no iron in the wire. There are no magnets near the compass. And yet the compass needle deflects when current flows through the wire and returns to its original position when the current is stopped. The electrical current in the wire is generating a magnetic field. Electricity is creating magnetism. Ørsted is, by all accounts, unsettled by this observation. He apparently does not fully trust what he has seen and says nothing about it for months. He conducts further experiments quietly, confirming the result repeatedly before he feels confident enough to publish. In July of 1820, he publishes a brief 4-page paper in Latin, Experimenta circa effectum conflictus electrici in acum magneticum. Experiments on the effect of electrical conflict on the magnetic needle. It is one of the most important 4 pages in the history of science. The response across Europe is immediate and explosive. Within weeks of Ørsted's paper circulating, laboratories across the continent are reproducing the experiment. The French physicist André-Marie Ampère reads about it, and within 2 weeks produces a comprehensive mathematical theory of the relationship. He demonstrates that 2 parallel wires carrying current in the same direction attract each other, and 2 wires carrying current in opposite directions repel. He establishes that magnetism is produced by the motion of electric charges. He formulates what becomes known as Ampère's law, describing the magnetic field produced by an electrical current in mathematical terms. The unit of electrical current, the ampere, the rate of flow of 1 coulomb of charge per second, is named for him. This discovery, that electricity and magnetism are linked, is the opening door to the entire modern electrical age. If electrical current produces magnetism, could magnetism produce electrical current? This is the question that haunts Faraday for the next 11 years. Part 8. Faraday and the Iron Ring, the greatest experiment in electrical history. Michael Faraday was born on the 22nd of September 1791 in Newington Butts, Surrey, in what is now part of South London. His father was a blacksmith. His family was poor. He received little formal education beyond reading and basic writing. At 14, he was apprenticed to a bookbinder and bookseller named George Rebow. And there, in the bindery, surrounded by books, Faraday did something that changed the course of science. He read them. He read everything he bound. He read encyclopedias on science. He read books on chemistry. He read Isaac Watts's treatise on education and the cultivation of the mind. And he began doing his own experiments, buying equipment with his tiny wages, conducting experiments in the back room of the shop, corresponding with other scientists. In 1812, a customer at the bookshop gave him tickets to attend 4 lectures at the Royal Institution by Humphrey Davy, the most celebrated chemist in England. Faraday attended all 4, took meticulous notes, bound them into a book, and sent the book to Davy with a letter asking for employment. Davy initially said there was nothing available. Then Davy dismissed an assistant for fighting and hired Faraday. Faraday was Davy's assistant from 1813. He travelled through Europe with Davy on a grand scientific tour. He became laboratory director of the Royal Institution in 1825. And throughout this period he experimented, constantly, obsessively. He conducted experiments the way a musician practices scales, daily, systematically, exploring variations with a patience and precision that astounded his contemporaries. He kept meticulous laboratory notebooks, numbered sequentially. Notebook entry number 17,050 is dated 1862, 5 years before his death, 49 years after he began keeping them. By the summer of 1831, Faraday has become convinced that if electrical current can produce magnetism, as Ørsted had shown, then magnetism ought to be able to produce electrical current. The symmetry of nature demands it. He can feel it, though he cannot yet prove it. On the 28th and 29th of August, 1831, he runs a series of experiments that will transform the world. He takes an iron ring, approximately 6 inches in diameter. He wraps one side of the ring with multiple coils of insulated copper wire, forming what he calls coil A. He wraps the other side with more coils of copper wire, coil B. The 2 coils are insulated from each other and from the iron ring. He connects coil A to a battery. He connects coil B to a galvanometer, a sensitive instrument for detecting current, and he watches. When Faraday connects the battery to coil A, current begins to flow. The current in coil A creates a magnetic field. The magnetic field passes through the iron ring. The iron ring guides and concentrates the magnetic field into coil B. The galvanometer needle in coil B deflects briefly, just a flicker, and then returns to 0. When Faraday disconnects the battery from coil A, the galvanometer needle deflects again, in the opposite direction, and returns to 0. It is not what he expected. He had expected a continuous current in coil B, while current flowed in coil A. Instead, he sees a transient pulse only when the current in coil A is changing, turning on or turning off. Faraday stares at the data. And he understands something that even he, with his intuitive genius, has not quite articulated before. It is not the presence of a magnetic field that induces current in a conductor. It is a changing magnetic field. A static magnetic field induces nothing. A moving, growing, or shrinking magnetic field induces current. Over the following months, Faraday conducts 135 separate experiments. He pushes a bar magnet in and out of a coil of wire and watches current flow. He moves a coil of wire near a stationary magnet and watches current flow. He builds a device now known as Faraday's disc, a copper disc rotating on an axle between the poles of a horseshoe magnet, with a wire touching the rim and a wire touching the center. This device produces the first steady, continuous, truly generated electrical current in history. It is the world's first electrical generator, the ancestor of every power station and dynamo on Earth. Faraday presents his findings to the Royal Society on the 24th of November, 1831. The principle he has discovered, electromagnetic induction, is expressed in what becomes known as Faraday's law. In words, whenever the magnetic flux through a circuit changes over time, an electromotive force, a voltage, is induced in that circuit. The induced voltage is proportional to the rate of change of magnetic flux with time. Expressed as a formula, the induced electromotive force equals the negative of the rate of change of magnetic flux over time. That is, the induced EMF equals negative d phi over dt, where phi represents the total magnetic flux through the circuit. The negative sign reflects what Heinrich Lenz would formalize in 1834 as Lenz's law, that the induced current always opposes the change that created it. Faraday also establishes in the same year that all forms of electricity, static electricity from friction, current electricity from batteries, electricity from his generator, electricity from thunderstorms, are identical. Not similar, not analogous, identical. The same phenomenon in different circumstances. This unification is as profound as Franklin's unification of lightning and sparks. Here is something remarkable about Michael Faraday. He never learned advanced mathematics. He understood no calculus, virtually no algebra beyond the most basic operations. Every single one of his discoveries, electromagnetic induction, the laws of electrolysis, diamagnetism, the concept of lines of force, the concept of the electromagnetic field, was arrived at through purely physical, experimental reasoning. He thought in pictures and forces and fields, not in equations. Albert Einstein, who understood something about thinking differently, kept a portrait of Faraday on the wall of his study, alongside portraits of Isaac Newton and James Clerk Maxwell. Ernest Rutherford, the man who discovered the atomic nucleus, called Faraday one of the greatest scientific discoverers of all time. But Faraday's greatest contribution may have been conceptual rather than experimental. In the 1830s and 40s, he develops the concept of the electromagnetic field. He proposes, against enormous resistance from colleagues who think in terms of direct action at a distance between particles, that forces are transmitted through a medium, through space itself, through what he calls lines of force. The magnet doesn't reach out and grab the compass needle directly. The magnet distorts the space around it. It creates a field. And it is that field, the magnetic field extending through space, that exerts force on the compass needle. Similarly, an electrically charged object creates an electric field in the space around it. It is the field that acts on other charged objects. This idea, the electromagnetic field is one of the most transformative concepts in the history of physics. It is what allows a 30-year-old Scottish physicist named James Clerk Maxwell to, in the 1860s, produce one of the supreme intellectual achievements of the 19th century. Part 9. Maxwell and the Equations that Revealed Light. James Clerk. Maxwell is born on the 13th of June, 1831. The same year, Faraday discovers electromagnetic induction. He grows up in Scotland, shows mathematical genius from childhood, and by the time he is 25, is already recognized as one of the greatest physicists alive. He has an extraordinary ability to take physical intuitions, like Faraday's lines of force, and translate them into rigorous mathematical language. Between 1861 and 1865, Maxwell publishes a series of papers that synthesize everything known about electricity and magnetism into a set of 4 equations. These are Maxwell's equations. They are, by almost universal consensus among physicists, among the greatest intellectual achievements in human history. They describe, with complete mathematical precision, the behavior of electric fields, magnetic fields, and their interactions with charge matter, in every situation, at every scale, everywhere in the universe. Let us describe each equation in words, because each one encodes a profound truth about reality. The first equation is Gauss's law for electricity. In words, electric field lines begin and end on electric charges. The total electric flux, the total flow of the electric field, through any closed surface is proportional to the total electric charge enclosed within that surface. A positive charge is a source of electric field lines. A negative charge is a sink. The second equation is Gauss's law for magnetism. In words, magnetic field lines form closed loops. They have no beginning and no end. There are no magnetic monopoles. Every magnet has both a north pole and a south pole. Cut a magnet in half and you get 2 smaller magnets, each with north and south poles. You cannot isolate a single magnetic charge the way you can isolate an electron. To this day, despite enormous theoretical motivation and experimental searches, no magnetic monopole has ever been confirmed to exist. The third equation is Faraday's law, formalized. In words, a changing magnetic field produces an electric field. The induced electromotive force around a closed loop equals the rate of change of the magnetic flux through the loop. This is Faraday's discovery rendered in mathematical form. The fourth equation is Ampere's law, modified. And here Maxwell makes his boldest and most extraordinary contribution. The original Ampere's law said, an electrical current produces a magnetic field. Maxwell asks, is electrical current the only thing that can produce a magnetic field? He thinks through a thought experiment involving a capacitor being charged. As charge builds up on the plates of a capacitor, there is no actual current flowing through the gap between the plates. no charge is moving across the gap. And yet, by symmetry with Faraday's law, by the deep intuition that the equations of nature should be symmetric, Maxwell proposes that a changing electric field in that gap should also produce a magnetic field, even in the complete absence of moving charges. He calls this extra term the displacement current. He adds it to Ampere's law. And then he does something extraordinary. He takes these four equations, with the displacement current term added, and finds that they can be combined into a single wave equation, a mathematical form describing a wave propagating through empty space. He calculates the speed of this wave from the constants that appear in the equations. The speed equals 1 divided by the square root of the product of the permittivity of free space and the permeability of free space. Expressed symbolically, C equals 1 divided by the square root of epsilon naught times mu naught, where epsilon naught is the permittivity of free space and mu naught is the permeability of free space. And when Maxwell plugs in the experimentally measured values of these constants, which had been measured independently in completely different experiments having nothing to do with light, he gets a wave speed of approximately 299,792,458 meters per second. He recognizes that number immediately. It is the speed of light. Within the margin of experimental error, the speed of the electromagnetic wave predicted by his equations is identical to the measured speed of light. And Maxwell draws the only possible conclusion. Light is an electromagnetic wave, not like an electromagnetic wave, not analogous to one. Light is oscillating electric and magnetic fields propagating through space at what we now call the speed of light. Every color your eyes can detect, every ultraviolet ray that burns your skin, every X-ray that photographs your bones, every microwave that heats your food, every radio wave that carries your voice across a continent, all of it is the same phenomenon, electromagnetic radiation. Different frequencies of the same kind of wave, all traveling at the same speed, all described by the same four equations. Maxwell publishes this prediction in 1864. He will not live to see it confirmed experimentally. He dies of abdominal cancer in 1879 at 48 years old. 8 years later, in 1887, a German physicist named Heinrich Hertz produces electromagnetic waves in his laboratory using an oscillating electric circuit and detects them at a receiver several meters away. He has produced and detected radio waves. Maxwell's prediction is confirmed. Hertz publishes his results. Within a decade, a young Italian inventor named Guglielmo Marconi is using Hertz's discovery to send wireless signals across the Atlantic. The entire telecommunications revolution, radio, television, cellular phones, Wi-Fi, GPS satellites, traces its lineage to Faraday's discovery of electromagnetic induction, and to Maxwell's four equations written on a piece of paper in Edinburgh in 1864. Part 10. Charles-Augustin de Coulomb and the Mathematics of Force. We should step back slightly because we have been following the thread of electromagnetic induction while neglecting another critical thread that was developing in parallel, the mathematical quantification of electrical force itself. Because understanding electricity is not only a matter of discovering new phenomena, it is also a matter of measuring and mathematizing the phenomena you already know about. And the man who does this most elegantly for the basic electrostatic force is a French military engineer named Charles-Augustin de Coulomb. Coulomb is born in Angoulême in 1736. He spends much of his career as a military engineer working on fortifications in Martinique, where he contracts a tropical illness that undermines his health for the rest of his life. But in the 1780s, now back in France, he turns his attention to a question that Franklin and others have noticed but not measured. How exactly does the force between two electrical charges depend on the distance between them and on the magnitudes of the charges? Coulomb builds an instrument of exquisite sensitivity called a torsion balance. He suspends a horizontal bar from a thin wire. One end of the bar carries a small charged ball. A second charged ball is brought near the first. The repulsion between the balls twists the bar, which twists the wire. The amount of twist, the torsion, measures the force. By systematically varying the charges and the distances and measuring the resulting forces, Coulomb establishes what becomes known as Coulomb's law. In words, the electrostatic force between two-point charges is directly proportional to the product of the magnitudes of the charges, and inversely proportional to the square of the distance between them. If you double the distance between two charges, the force drops to 1/4. If you triple the distance, the force drops to 1/9. If you double one of the charges, the force doubles. If you double both charges, the force quadruples. The mathematical form is F equals K sub E multiplied by Q1 multiplied by Q2, all divided by R squared. Where F is the force, K sub E is Coulomb's constant, approximately 8.99 times 10 to the power of 9 Newton square meters per Coulomb squared. Q1 and Q2 are the magnitudes of the two charges, and R is the distance between them. This is the same mathematical form as Newton's law of universal gravitation, which states that gravitational force equals G times m1 times m2 divided by r squared. Both are inverse square laws. This deep structural similarity between gravity and electrostatics fascinated physicists throughout the 19th century, and eventually, through general relativity and quantum field theory, led to the ongoing project of unifying all the fundamental forces, a project that is still incomplete today in 2026. Coulomb's law is published in 1785. It allows, for the first time, precise quantitative predictions of electrical forces. It is the foundation of electrostatics as a quantitative science, and it gives physicists the conceptual scaffolding to start thinking about electricity not just as a strange phenomenon, but as something subject to precise mathematical laws, something that can be predicted, calculated, engineered. Part 11. Ohm's Law and the Mathematics of Current. The humble beginning of circuit theory. In 1827, a German high school teacher named Georg Simon Ohm publishes one of the most practically important relationships in all of electrical science. He publishes it in a book that is almost completely ignored for years. The Prussian Ministry of Education is reportedly so unimpressed that Ohm loses his teaching position. He struggles financially for years, and his discovery, now known to every schoolchild in the world as Ohm's law, eventually earns him the Copley Medal of the Royal Society and immortality. Ohm's insight is this: the current flowing through a conductor between 2 points is directly proportional to the voltage, the electrical potential difference, across those 2 points, provided the temperature and other physical conditions remain constant. The proportionality constant is the resistance of the conductor. Expressed in the formula V equals I times R, voltage equals current times resistance. V is measured in volts, I in amperes, R in ohms. The unit of resistance, the ohm, is named for him. It is represented by the capital Greek letter omega. To understand what this means physically, consider the analogy of water flowing through a pipe. The voltage is like the water pressure. It drives the flow. The current is like the flow rate. How much charge passes a point per unit of time. The resistance is like the narrowness of the pipe. How much the pipe impedes the flow. A wide pipe with high pressure will have a large flow rate. A narrow pipe with low pressure will have a small flow rate. This analogy, while imperfect, captures the essential relationship. Ohm's law is the fundamental relationship that makes all of circuit design possible. Every circuit in every device you own, from your phone to your car to the satellites in orbit, is designed with Ohm's law as a foundational principle. Ohm also describes, in the same work, what we now call resistivity, the property of materials that determines how much they resist the flow of electricity. Metals have low resistivity. Copper, silver and gold are excellent conductors. Rubber, glass and ceramics have extremely high resistivity. They are excellent insulators. Silicon and germanium have intermediate resistivity. They are semiconductors, and this intermediate property will, a century later, give us the transistor and the entire digital revolution. Georg Ohm died in 1854. He lived just long enough to see his law accepted and his genius recognized. He taught in a high school for years after his greatest discovery, waiting for the world to understand what he had done. Part 12, The War of Currents, Edison, Tesla, and the battle that lit the world by the 1870s. Electricity has moved from the laboratory into the world. The telegraph already uses electrical signals to communicate across continents. The first arc lamps are providing brutal blue-white light to public spaces, too harsh and too impractical for homes, but dazzling as street lighting. But the next step, bringing practical electrical light into ordinary homes and businesses, requires solving two interrelated problems. First, you need a light source that is practical, long-lasting and affordable. Second, you need a system to deliver electrical power to that light source at scale. The man who attacks both problems simultaneously with a combination of genius and industrial ruthlessness is Thomas Alva Edison. Edison is born in 1847 in Milan, Ohio. He has almost no formal schooling. His mother teaches him at home after a teacher reportedly describes the young Edison as addled. He begins working as a telegraph operator at 15 and discovers in himself an almost supernatural capacity for technological problem-solving and relentless, systematic experimentation. By his 30s, he has already invented the phonograph and made significant improvements to the telegraph. He establishes the world's first industrial research laboratory in Menlo Park, New Jersey. A building staffed by dozens of researchers working specifically on invention as an organized industrial process. Edison famously describes his method as 1% inspiration, 99% perspiration. The laboratory confirms this. In 1879, Edison focuses on the incandescent light bulb. The concept is not new. Other inventors, including Joseph Swan in England, are working on similar devices simultaneously. The principle is simple. Pass electrical current through a thin filament of material, and if the resistance is high enough, the filament glows. The problem is that almost every material tried either burns up immediately or fails quickly. The filament must glow without oxidizing, which means it must be in a vacuum, and it must be thin enough to have high resistance, so it glows brightly, but strong enough to withstand continuous use. Edison and his team test thousands of materials for the filament. They test carbonized versions of hundreds of plant fibers. On the 22nd of October, 1879, Edison tests a carbonized cotton thread filament in an evacuated glass bulb. It glows for 13.5 hours before burning out. He keeps improving. By the end of that year, he has bulbs that last over 1,000 hours. He demonstrates his system publicly in Menlo Park on the 31st of December, 1879, lighting the laboratory and surrounding roads with 40 electric lamps. Reporters from newspapers across the country attend. The New York Herald publishes the story under the headline, Edison's Light, the Great Inventor's Triumph in Electric Illumination. But the light bulb is only half the problem. To be useful, bulbs need electricity. And in 1879, the only way to get electricity is from a battery. Expensive, heavy, impractical for domestic use at scale. Edison needs to build a system. Not just a light, a power station, a distribution network, meters, switches, circuits, the entire infrastructure of an electrical civilization that does not yet exist. He designs it from scratch. In 1882, Edison opens the Pearl Street station in Lower Manhattan. The world's first central commercial electrical power station. It uses direct current, DC, generators powered by steam engines. It serves 59 initial customers in a roughly 1 square mile area of Lower Manhattan. Within 14 months, it is serving 508 customers and powering over 10,000 light bulbs. The electrical age, in practical terms, has begun. But Edison's direct current system has a fatal flaw, and a young Croatian-American engineer named Nikola Tesla is about to expose it. Direct current, DC, flows in one direction only. The voltage of DC cannot be easily changed using the transformers of the era. This means you cannot efficiently transmit DC over long distances. As current flows through a wire, it loses energy to the resistance of the wire. This is described by what is called Joule's law, discovered by the English physicist James Prescott Joule in 1840. Joule's law states that the power dissipated as heat in a conductor equals the current squared multiplied by the resistance, expressed as P equals I squared times R. To minimize these losses, you need to transmit at very high voltage and very low current. But Edison's DC system operates at 110 volts, which means power stations need to be within roughly 1.5 miles of their customers. Otherwise, too much power is lost to resistance heating in the wires. Tesla arrives in America in 1884 and works briefly for Edison before the two part ways in circumstances that are still disputed. What is not disputed is that Tesla had already, in 1882, conceived of a revolutionary approach to electrical power generation and transmission, alternating current. In an alternating current, AC system, the direction of current flow reverses periodically. In the systems that power most of the world today, current reverses 50 or 60 times per second. 50 Hz in most of Europe and Asia, 60 Hz in North America. At any given moment in an AC circuit, the current is flowing one way. Half a cycle later, it is flowing the other way. The crucial advantage of AC over DC is transformers. A transformer, the device that Faraday's principle of electromagnetic induction makes possible, as our sound can step voltage up or down with very high efficiency. At a power station, AC voltage can be stepped up to hundreds of thousands of volts for long-distance transmission. At this very high voltage, the current is very low, and since power losses are proportional to current squared, from Joule's law, the losses drop dramatically. Near the point of use, a second transformer steps the voltage back down to safe levels, 110 or 220 volts. This means one power station can serve customers across an entire region, even across hundreds of miles, with acceptable losses. Edison's DC stations needed to be within 1.5 miles of their customers. Tesla's AC system could theoretically transmit power across continents. Edison understands the threat. He launches a campaign, now known as the War of Currents, to discredit AC power. He hires a technician named Harold Brown to travel around New York State, publicly electrocuting dogs, calves, and eventually a horse using AC current to demonstrate its lethal dangers. He lobbies state governments. He spreads misinformation about safety. He argues with the passion of a man who has invested enormous capital in DC infrastructure that AC is too dangerous for public use. In the most infamous episode of the campaign, the first electric chair execution at Auburn Prison in New York in 1890 is conducted using an AC generator. And Edison, in a piece of dark irony he apparently considers tactically brilliant, suggests that the act of electrocuting someone be called being Westinghoused, after George Westinghouse, who had partnered with Tesla and was championing AC. Westinghouse refuses to use the term. No one else does either. The War of Currents is decided at Niagara Falls in 1893. The Niagara Falls Power Company awards a contract for a hydroelectric generating system. Tesla and Westinghouse win the contract against Edison. In 1895, the Niagara Falls power station begins generating electricity using Tesla's AC polyphase system. By 1896, AC power is being transmitted 22 miles to the city of Buffalo, New York, lighting it completely, powering its industries. The longest DC transmission of the era would have covered barely 2 miles. AC wins definitively, completely. The electrical infrastructure of the modern world is built on alternating current. Tesla is a figure of almost mythological dimensions in the history of electricity. His contributions are staggering. He develops the AC polyphase system, the system that allows the efficient transmission and use of power in multiple simultaneous alternating current phases. He invents the AC motor. He invents the Tesla coil, a resonant transformer circuit that produces very high voltage, high frequency, alternating current, which is used in radio technology and still demonstrates the principles of electromagnetic resonance in physics classrooms today. He holds over 300 patents. He conceives, at the turn of the 20th century, of wireless power transmission. The idea of sending electrical energy through the air without wires, an idea he pursues in his Wardenclyffe Tower project before running out of funding. The unit of magnetic flux density, the Tesla, is named for him. He died in 1943 in a New York hotel room, nearly penniless, having transferred or lost control of most of his patents. Part 13. The electron. Discovering the particle behind the force. We have told an extraordinary story of discovery. But through all of it, through Thales rubbing amber, through Franklin flying his kite, through Faraday rotating his disk, through Tesla designing his generators, nobody knew what electricity actually was. Nobody knew what the substance of electrical charge was made of. What was actually flowing when current flowed. What actually accumulated when charge built up. What, physically, was electricity? The answer comes in 1897 from a laboratory in Cambridge, England. J.J. Thomson, Joseph John Thomson, is the Cavendish Professor of Experimental Physics at the University of Cambridge. He is studying the behavior of what are called cathode rays, streams of something that emerge from the negative electrode, cathode, of an evacuated glass tube when a high voltage is applied across it. For decades, physicists have debated what cathode rays are. German physicists largely believe they are waves, similar to light. British and French physicists suspect they might be charged particles. Thomson builds cathode ray tubes with electric and magnetic deflection fields. He passes cathode rays through electric fields and observes them deflecting, confirming they carry charge. He applies magnetic fields and observes the deflection in a magnetic field. From the combination of electric and magnetic deflections, he can calculate two things: the speed of the rays and the ratio of their charge to their mass, the charge-to-mass ratio. He expresses this ratio as E divided by m, where E is the charge and m is the mass. The charge-to-mass ratio Thomson measures is approximately 1.76 times 10 to the power of 11 coulombs per kilogram. It is the same regardless of what the cathode is made of. It is the same regardless of what gas fills the tube before evacuation. It is the same regardless of the voltage applied. Thomson deduces that cathode rays consist of particles that are a universal constituent of all matter, the same particle, everywhere, in everything. And from the charge-to-mass ratio, compared to known values for ions, he deduces that these particles are extraordinarily light, roughly 1,836 times lighter than a hydrogen atom, which is itself the lightest atom known. Thomson announces his discovery on the 30th of April, 1897, in a lecture to the Royal Institution. He calls the particles corpuscles. The name does not stick. They become known as electrons, the very word Thales had given amber 2,300 years earlier. The same word that Gilbert had adapted to give electricity its name. The particle was named for the stone that first revealed it to human notice. The discovery of the electron answers definitively the question of what electricity is. Electricity is the flow of electrons, or more precisely, the movement of electric charge, which is carried by electrons in most everyday contexts. When you rub amber against fur, electrons transfer from the fur to the amber. The amber gains extra electrons and becomes negatively charged. When current flows through a wire, it is electrons, billions upon billions of them, migrating through the metallic lattice of the wire in response to an electric field. The fluid that Franklin imagined, the animal electricity that Galvani proposed, the force that Thales observed in amber, all of it, at its deepest level, is the behavior of electrons. The electron has a charge of negative 1.602176634 times 10 to the power of negative 19 coulombs. This is called the elementary charge, the smallest unit of charge that exists in ordinary matter. All charges, positive or negative, are integer multiples of this value. The electron has a mass of 9.109388 times 10 to the power of negative 31 kilograms, which is such a small number that it requires a moment of genuine pause. One electron is approximately 9.1 times 10 to the negative 31st kilograms. To put this in context, if you could line up electrons side by side, it would take approximately 25 million electrons to span the width of a single human hair. Thomson receives the Nobel Prize in Physics in 1906 in recognition of the great merits of his thorough and experimental investigations on the conduction of electricity by gases. His son, George Paget Thomson, also wins the Nobel Prize in Physics in 1937 for demonstrating that the very same electron his father discovered as a particle also behaves as a wave, exhibiting diffraction when it passes through a crystal. Father and son, particle and wave. The same electron showing different faces to different experiments. This is quantum mechanics beginning to devour classical physics. Part 14. The photoelectric effect, Einstein, photons, and the quantum revolution. In 1887, Heinrich Hertz, the man who confirmed Maxwell's electromagnetic waves, notices something odd during his radio wave experiments. When ultraviolet light falls on a metal electrode, the electrode emits charged particles more easily. He reports the observation, but does not explain it. In the following years, other physicists, including Philippe Lenard, who will win a Nobel Prize for the work, study the effect more carefully. They call it the photoelectric effect. Metal illuminated by light emits electrons. What is strange about the photoelectric effect is not that it occurs. What is strange is how it occurs. Classical physics, Maxwell's electromagnetic theory, predicts that whether electrons are ejected from a metal should depend on the intensity of the light. Brighter light should eject more electrons with more energy. But experiments show something completely different. Dim light of a short enough wavelength will immediately eject electrons with high energy. Bright light of a long wavelength will eject no electrons at all, no matter how long you wait, no matter how intense the light becomes. The energy of the ejected electrons depends on the wavelength, the color of the light, not on its intensity. Classical physics cannot explain this. In 1905, the same miraculous year in which he publishes Special Relativity and Brownian Motion, a 26-year-old patent clerk named Albert Einstein publishes a paper titled On a Heuristic Point of View Concerning the Production and Transformation of Light. In it, he proposes that light is not a continuous wave, but is quantized, that it consists of discrete packets of energy that he calls light quanta. These quanta are later called photons. Each photon carries an energy equal to Planck's constant multiplied by the frequency of the light, expressed as E equals h times f, where h is Planck's constant, approximately 6.6 to 6 times 10 to the power of negative 34 joule seconds, and f is the frequency in hertz. The photoelectric effect is then explained simply. A photon of light hits the metal surface. If the photon has enough energy, which depends on its frequency, not on the total brightness of the light, it can kick an electron out of the metal. If the photon doesn't have enough energy, no electron is emitted, no matter how many such photons you throw at the surface. It is like trying to knock a bowling pin over by throwing feathers at it. You can throw millions of feathers and achieve nothing, but one rock of sufficient weight will do the job. The photon is the rock. The electron is the pin. This paper, for which Einstein receives the Nobel Prize in Physics in 1921, does not merely explain the photoelectric effect. It reveals that light, which Maxwell had triumphantly shown to be an electromagnetic wave, is also in some sense a particle. And by extension, it suggests that the boundary between waves and particles, the boundary that classical physics had considered absolute and obvious, is not a real boundary at all. It is the opening shot of the quantum revolution. The revolution that will, within 30 years, give us quantum mechanics, which describes the behavior of electrons, photons, and all subatomic particles with a precision that has never been equaled in the history of science. The photoelectric effect is also, incidentally, the physical principle underlying solar panels, the photovoltaic devices that today cover hillsides, rooftops, and vast desert farms across the world. When photons of sufficient energy strike a semiconductor material like silicon, they knock electrons loose, creating electrical current. The first practical solar cell was built in 1954 at Bell Labs. As of 2025, solar power is the least expensive source of electrical energy that has ever existed in human history. A discovery that Einstein made in 1905 to explain a laboratory. Curiosity is now reshaping the global energy system. Part 15. The structure of the atom and the deeper nature of electrical charge. Thomson discovered the electron in 1897. He proposed a model of the atom that placed electrons distributed throughout a diffuse, positively charged sphere, like raisins distributed through a pudding. This became known, with gentle British humour, as the plum pudding model. It was wrong, and the experiment that proved it wrong, conducted in 1909 and 1911 under Ernest Rutherford at the University of Manchester, revealed a truth about the atom that was, in Rutherford's own words, as if you fired artillery shells at tissue paper and they came back and hit you. Rutherford directed Hans Geiger and Ernest Marsden to fire alpha particles, helium nuclei, positively charged, at a thin sheet of gold foil. If the plum pudding model were correct, the diffuse positive charge of the atom would barely deflect the alpha particles. They should pass almost straight through. Most do, but a small fraction, about 1 in 8,000, bounce back at large angles. Some come almost straight back. The only way this can happen is if the positive charge of the atom is concentrated in an extremely small, extremely dense central region. Rutherford calls it the nucleus. The atom, it turns out, is almost entirely empty space. The nucleus occupies a volume roughly 100,000 times smaller than the total volume of the atom, like a marble placed in the center of a football stadium, while the electrons orbit somewhere in the stands. The nucleus contains positively charged protons and electrically neutral neutrons, the neutron being discovered by James Chadwick in 1932. The positive charge of the nucleus is determined by the number of protons. The negative charge of the surrounding electrons in a neutral atom exactly balances the positive charge of the nucleus. The charge of a proton is exactly equal in magnitude to the charge of an electron, 1.602176634 times 10 to the negative 19th coulombs, but positive. This equality is one of the most precisely confirmed facts in all of physics. It has been measured to better than 1 part in 10 to the 21st power. Nobody knows why the charge of the proton is exactly equal and opposite to the charge of the electron. These are particles of vastly different masses, composed of completely different fundamental constituents. Protons are made of quarks. Electrons are, as far as we know, fundamental. Yet their charges are perfectly matched. This is one of the deep, unresolved mysteries of fundamental physics. The deeper understanding of charge that emerges from 20th century physics is that electric charge is a quantum number, a discrete, conserved property of matter. Charge is conserved. The total electric charge in any isolated system never changes. You can separate charges, pull positive and negative apart, but you cannot create charge or destroy it. Every process that has ever been observed, from the collision of elementary particles in the Large Hadron Collider to the chemical reactions in a battery to the firing of a neuron in your brain, conserves electric charge exactly. At the deepest level we currently understand, electromagnetism, the force that encompasses all of electricity and magnetism, is mediated by the photon. When two charged particles interact, they exchange photons. These are not ordinary light photons that you could detect with your eye. They are what physicists call virtual photons, quantum mechanical entities that exist within the energy-time uncertainty prescribed by Heisenberg's uncertainty principle. The exchange of virtual photons is what produces the electromagnetic force between charges. This is described by quantum electrodynamics, QED, the theory developed by Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga in the 1940s and 50s. QED is the most precisely tested theory in all of science. Its predictions have been confirmed to extraordinary accuracy. Its calculations of the magnetic moment of the electron agree with experimental measurements to 1 part in 10 to the 12th power. 1 part in a trillion. To achieve that level of agreement would be like predicting the distance between New York and Los Angeles to within the thickness of a human hair. Part 16. From discovery to civilization, the world electricity built. Let us step back and take the full measure of the journey. In 600 before the Common Era, a Greek philosopher rubbed amber against fur and wondered why dust stuck to it. He had no concept of charge, no concept of electrons, no concept of electromagnetic force. He watched the amber attract a feather, and he was astonished, and he wrote it down, and he theorized, incorrectly, that it was the amber's soul. In 1820, a Danish professor watched a compass needle deflect near a wire carrying current, and he was so uncertain of what he had seen that he waited months before telling anyone. The deflection of that compass needle, electromagnetic induction, the relationship between electricity and magnetism, is the principle that makes it possible to generate electricity by spinning a coil of wire in a magnetic field. Every power station on Earth operates on this principle. Every hydroelectric dam, every wind turbine, every nuclear plant. They all, at their core, spin a conductor in a magnetic field. They are all, at their core, Michael Faraday's copper disc from 1831, scaled up to industrial proportions. Consider what electricity has built in the roughly 150 years since it was first delivered to homes. Refrigeration, which saves more lives annually from foodborne illness than almost any other technology. Electric lighting, which extended the productive hours of human civilization by roughly half. Before artificial light, darkness was the end of the workday for most of the world's population. Electric motors, which have displaced human and animal labor across virtually every industry. Radio and telecommunications, which, as we have seen, flow directly from Maxwell's equations and Hertz's experimental confirmation. Computers, built on transistors, which are semiconductor devices that exploit the quantum mechanical properties of electrons, which have transformed every domain of human activity. Medical imaging, X-rays, MRI, PET scans, all based on electromagnetic phenomena. The Internet, which is light encoded in electromagnetic waves and electrons moving through copper and glass. As of 2024, global electricity generation is approximately 30,000 terawatt-hours per year. A terawatt-hour is 1 trillion watt-hours. Approximately 63% of this electricity is generated from fossil fuels. But this is changing with extraordinary speed. In 2024 alone, the world installed new renewable energy generation, equivalent to roughly 100 nuclear power plants. Solar power, operating on Einstein's photoelectric effect, is now the cheapest source of electricity in human history. Wind turbines operate on Faraday's electromagnetic induction. The battery storage systems that buffer renewable energy operate on Volta's electrochemical principles. The entire transition to renewable energy is, in a fundamental sense, the second and third chapters of discoveries that began with Thales and amber and frog legs in a Bologna laboratory. Part 17. What we still do not know, for all that we have discovered, for all the precision of quantum electrodynamics, for all the engineering mastery encoded in the global electrical grid, there are things we still do not understand. We do not know why the charge of the proton and the charge of the electron are exactly equal in magnitude. This equality is one of the deepest and most mysterious facts in physics. It is not predicted by any existing theory. It is simply measured, confirmed to extraordinary precision, and unexplained. We do not have a complete theory that unifies electromagnetism with gravity. Maxwell's equations and Einstein's general relativity are both extraordinarily accurate theories in their respective domains. They are mathematically incompatible. The electrostatic force between two electrons is approximately 42 powers of 10 times stronger than the gravitational force between them. Yet gravity controls the large-scale structure of the universe, and electromagnetism governs atomic and molecular behavior. Why this enormous disparity? The hierarchy problem, the question of why gravity is so absurdly weak compared to electromagnetism, is one of the central unsolved problems of theoretical physics. We do not fully understand the physical mechanism of contact electrification, the very phenomenon that Thales observed when he rubbed amber. In March of 2025, a new paper from physicists demonstrated that contact electrification depends in subtle ways on the previous contact history of the materials involved, that the surface memory of a material affects how charge is transferred. In September of 2024, researchers explained for the first time how rubbing a surface creates electrical current at the molecular level. These are active research questions in 2025 and 2026. The phenomenon that started the entire story, amber attracting dust, still contains scientific puzzles that we are actively working to solve. We do not fully understand how lightning initiates. We know the general conditions: charge separation in thunderclouds, the accumulation of enormous potential differences, the breakdown of air as a conductor when the field is strong enough. But the precise mechanism of how the discharge initiates, the spark that starts the bolt, involves complex microphysics of ice crystals, supercooled water droplets, and graupel that is still not completely understood. In November of 2025, researchers at the University of something were using laser traps to suspend single aerosol particles and study exactly how they charge up, watching each individual step in the electrification process. The thing that Franklin proved was electrical in 1752 is still under active scientific investigation in 2026. And at the frontier of quantum mechanics, entirely new electrical phenomena are being discovered. In October of 2025, researchers in Japan reported a strange quantum metal in which weak magnetic fields can reverse tiny electrical currents, behavior that rewrites the classical rules of how magnetism and electricity interact in these exotic materials called kagome metals, which have a woven atomic structure unlike anything in conventional materials science. In November of 2025, engineers at the University of Delaware uncovered a new way to bridge magnetism and electricity through magnons. Tiny waves that carry information as magnetic spin disturbances without any electrical current flowing at all. The boundaries of what we know about electricity are being expanded almost daily in laboratories around the world. Part 18. The body electric, electricity in life itself. Let us return at the end of this story to where we began, to the electricity inside you. Every cell in your body maintains a voltage across its membrane. The inside of a typical cell is approximately -70 millivolts relative to the outside, roughly 1/14 of the voltage of a AA battery. This resting membrane potential is maintained by ion pumps, protein machines embedded in the cell membrane that actively move sodium ions out of the cell and potassium ions in, powered by the chemical energy molecule adenosine triphosphate, or ATP. The difference in ion concentration across the membrane and the selective permeability of the membrane to different ions creates the electrical potential. In nerve cells, neurons, this resting potential can be disrupted. When a stimulus arrives, a touch, a chemical signal, an incoming signal from another neuron, ion channels in the membrane open. Sodium ions flood in. The voltage rapidly reverses from -70 millivolts to approximately +40 millivolts in about 1 millisecond. This is called an action potential. It propagates along the length of the neuron, racing from one end to the other at speeds ranging from roughly half a meter per second in thin, unmyelinated fibers to over 100 meters per second in thick, insulated fibers. At the end of the neuron, the action potential triggers the release of chemical neurotransmitters across the synapse, the gap, to the next neuron or muscle fiber. You are, electrically speaking, a network of about 86 billion neurons, each one communicating through precisely timed electrical signals. Every thought you have ever had was an electrical pattern. Every memory, every sensation, every emotion, the action potential of joy and the action potential of grief are both, at their most fundamental physical level, the movement of sodium and potassium ions across a lipid bilayer membrane. Your consciousness, whatever it is, however we eventually come to understand it, arises from electrical activity. Galvani, for all his errors about animal electricity, was pointing at something profound and real. The sinoatrial node, the natural pacemaker of the heart, generates electrical impulses through a specialized mechanism. Unlike most cells, pacemaker cells spontaneously depolarize. Their membrane potential drifts upward from about -60 millivolts to a threshold around -40 millivolts, at which point an action potential fires and the current spreads through the heart muscle, triggering a coordinated contraction. This happens 60 to 100 times per minute, every minute, continuously, from before you are born until the moment you die. It requires no conscious effort. It requires no external input. It is electricity running continuously in your chest, keeping you alive. When it stops, when the organized electrical activity of the heart is replaced by chaotic, uncoordinated firing called ventricular fibrillation, a defibrillator delivers a shock of several hundred joules to the chest. The shock depolarizes all heart muscle cells simultaneously, briefly stopping the heart entirely. In this brief electrical silence, the natural pacemaker can reassert organized rhythm. You restart a heart with electricity. Giovanni Aldini's grotesque demonstrations on corpses in London in 1803, making a dead man's arm rise, his eye open, were not science fiction. They were crude, dangerous versions of what emergency medicine does routinely, successfully, hundreds of thousands of times a year. Part 19. The Full Circle. We have travelled in this story from amber on the Aegean coast to quantum kagome metals in a Japanese laboratory. From a Greek philosopher wondering why a stone attracts dust, to equations describing the force between electrons to a precision of 1 part in a trillion. From dead frog legs twitching in Bologna to the electrical signals running through 86 billion neurons in a human brain. From a printer flying a kite in a Philadelphia storm to the global electrical grid that, as of 2024, delivers electricity to approximately 8 billion people. What does this story tell us? It tells us that the greatest discoveries in the history of science have never been the result of a single genius working in isolation. They are the accumulated result of hundreds of men and women across dozens of countries over centuries, each one building on what came before, each one seeing a little further because they were standing on the shoulders of the people who came before them. Thales saw amber attract dust and wrote it down. Gilbert read what Thales wrote and gave the phenomenon a name. Guericke built a machine and saw that charge repels as well as attracts. Gray discovered that charge travels. Dufay discovered that there are 2 kinds. Franklin unified lightning and sparks. Galvani made dead legs twitch. Volta built a battery. Ørsted moved a compass needle. Faraday rotated a disk. Maxwell wrote 4 equations. Hertz confirmed them. Thomson found the electron. Einstein explained the photoelectric effect. Bohr and Schrödinger and Heisenberg and Dirac built quantum mechanics. Feynman wrote QED. No single one of these people could have done what all of them together did. and all of them together across 2,600 years could not have predicted what the world looks like today as a result of their curiosity. In 600 before the Common Era, Thales of Miletus picked up a piece of amber and rubbed it against fur. He could not have known. He could not possibly have known that the invisible force he felt pulling dust toward the stone was the force that holds every atom in every object in the universe together. That it was the force that fires every signal in every nervous system on Earth. That it was the force that 2,600 years later would power the cities and the hospitals and the computers and the satellites and the global communications network that makes human civilization possible. He just rubbed a stone against fur. He saw something strange. He wondered about it. He wrote it down. That act of looking, wondering, and writing it down is how electricity was discovered. Not in a single moment, not by a single genius, but in 10,000 moments of curiosity accumulated across 2.5 millennia by human beings who looked at the world and refused to look away. Right now, as you hear these words, electrical signals are moving through the neurons in your auditory cortex, organizing themselves into meaning. Your heart is beating because of an electrical signal generated in cells that have been doing this, uninterrupted since before you took your first breath. Every device around you, everything that runs on power, everything with a screen, everything that makes modern life recognizable as modern life, is a consequence of those 10,000 moments of curiosity, of Thales and his amber, of Galvani and his frog, of Faraday and his iron ring, of Maxwell and his equations. You are alive because of electricity. You are reading this because of electricity. The civilization that produced the language you think in, the alphabet you read in, the infrastructure that keeps you fed and warm and connected, all of it runs on electricity. And it all began with a piece of golden stone and a moment of wonder on a coast in ancient Greece. 2,600 years ago, a stone, some fur, and an invisible force that would eventually own everything. That is how electricity was discovered.